Let's take a look now at the properties of real numbers. There's a lot of properties of real numbers that we are familiar with and which we take for granted. However, when we study algebra, one thing we're going to be looking at will be expressions and equations that involve variables. With variables, you don't know what the value of that number is. So, for example, if I say 2 plus 7, okay, well, we know that's 9. We can always count up if we need to. 7 plus 2, 7, 8, 9. If we say 3 times 2 plus 7, well, again, we can follow the order of operations. 2 plus 7 make 9. Everything in the parentheses goes first. And then we're going to multiply that times 3. And 3 times 9 would be 27. And those are all possible because of properties of numbers that we know the order of operations, we know how addition and multiplication work. But what happens when you start having some of these not be constant numbers? What happens when we replace one of these with a variable like x or y or z? Well, we can still perform these actions, but it's a little harder since we don't know the identity of the numbers. So what we want to do is we want to divorce the property of numbers from the numbers themselves. Rather, we want to know how numbers behave regardless of whether or not we know what the numbers happen to be. So we're going to take a look at a few properties which, again, we've seen before and which are taken for granted ever since you learned basic addition and subtraction. But here we want to name them and highlight what they are so that when we start seeing them with variables rather than constants, they're a little more familiar for us to use. So we're going to begin with what's called commutativity. So let's talk about commutativity. The commutative property, and really I should say properties because there's several of them. The commutative properties state the following. Let's say you have two real numbers. Let A and B be real numbers. Notice that we don't know what A and B are other than they're real numbers. We don't know that that's 5 and 7 or 2 and 9 or anything else. We just know that they are real numbers. But that's enough. Because for any real numbers, the following statements are true. The first one is the commutative property for addition, which states that if you take those two numbers and add them together in this order, that's exactly the same as if you were to add them together in the second order here. A plus B is the same as B plus A. And this is the commutative property for addition. Multiplication is the same. If you have A times B, that's the same as B times A. And this will be true of any numbers you can think of. So, for example, you could say 2 plus 5 is the same as 5 plus 2. You could say 11 times 50 is the same as 50 times 11. It doesn't matter what order things are multiplied in, and it doesn't matter what order things are added in. The order for addition and multiplication do not matter. Now, keep in mind that this does not apply to subtraction and division unless we rewrite it as addition or multiplication. What I mean by that is, here, note, subtraction and division are not commutative, meaning that you can't just switch the order, which commutative, but we can get around that by rewriting subtraction as addition and by rewriting division as multiplication. So for example, if I have 5 plus 7, that's the same as 7 plus 5. And that's just an example of the commutative property of addition. Now, if I have 5 minus 7, I can't just rewrite that as 7 minus 5, right? Because this would be a negative number, whereas 7 minus 5 would be a positive number. But what we can do is we can rewrite this using addition. Subtracting 7 is the same as adding a negative 7. Oh, but now that it's addition, now we can use commutativity to say negative 7 plus 5, like that. So subtraction is not commutative, but if you write it as addition, that addition is commutative. Right? Same thing with multiplication. If I have 10 times 5, That's equal to 2. Right? And that's the same as, it's equal to 2. Is equal to 50. I was thinking of division here for a second. Is equal to 50, which is the same as 5 times 10. Note that doesn't make a difference. 10 times 5 or 5 times 10. Both of those are equal to 50. But if I write that as division, 10 divided by 5, that is not commutative. I can't switch the order of these. 10 divided by 5 would be 2. But 5 divided by 10 would not be 2. It would be a half. Okay, but just like with subtraction, I can rewrite that as addition. With division, I can rewrite it as multiplication. Because remember, dividing by a number is the same as multiplying by its reciprocal. So that's 10 times 1/5. And now that it's written as multiplication, now you can rewrite that in any order you like. Just like that. So this is, oh, and I realize I've misspelled the name here. The commutive properties, my apologies. The commutative properties. There we go. The commutative properties of addition and multiplication. Okay. Another property of real numbers is the associative property. So let's take a look at those. The associative, okay, I got it right that time. The associative properties. And again, there's two of those, one for addition and one for multiplication, just like for the commutative properties. The commutive properties, commutative. I like to joke that since English is my second language, that's why I'm bad at spelling, because I've only been speaking English for, 30 years now? So I haven't had enough time to learn spelling. All right. So the associative properties, again, there's two of them, just like with the commutative properties, addition and multiplication. And that is, if you add things together, and again, we don't really care what those numbers are, so here we're just going to say let A, B, and C be real numbers. Any real numbers will do. Then A plus B plus C is equal to A plus B plus C, regardless of how we group things. So if you say A plus B first and then C, or if you say B plus C first and then A, these still mean the same thing. Multiplication has an associative property as well. A times B times C is equal to A times B times C, regardless of what order we multiply these in. So if we multiply A times B first and then C, or if we say B times C first and then A, it doesn't matter. These are going to be the same no matter what. Note that because this is going to work for any real numbers, and that includes variable numbers, because those are real, we just don't know exactly what they are, they can change. The associative property can be used for any addition, even if we don't know exactly what any or all of those numbers happen to be. So, for example here, let's say I was going to add together x plus 5 plus 9. Okay? Now, the order of operations tells me I have to do this first. Problem is I can't, because, well, I don't know what x is. I can't add it to 5 because I don't know what I'm adding. But the associative property lets me rearrange and regroup. Meaning, instead of x plus 5 and then plus 9, I could do these first. I could say 5 plus 9 first, and then add the x in. That's what this one says. I can either have these grouped or these grouped. But now, by having these grouped, I know how to do this. 9 plus 5 will give me 14. Now, I still can't add the x to the 14, but at least now it's simplified. I have fewer numbers and less operations. Here I had 2 additions and parentheses. Here I just have a single addition. This will be something we use a lot, and this is referred to as simplifying an expression. We'll define that a little bit more thoroughly in the later on in this video. When we simplify an expression, we're using the properties that we are going to be talking about, the commutative properties, the associative properties, and a couple of others, which we'll see here momentarily, to take operations and reduce the number of operations, reduce the number of terms, until nothing else can be reduced, until everything is as simple as we can write it. Now, when your expression involves a variable, sometimes you won't be able to get it down to a single term, but we try to get it down to as small as we can. Likewise with multiplication, if we had 2 times 3x, well again, order of operations tells me I'm supposed to multiply those first. But I can't because I don't know what x is. So 3 times x is, well, it's 3 times x. I'm not sure what else to do. But the associative property allows me to regroup this. So that instead of saying 2 times 3 times x, the quantity 3 times x, I can say the quantity 2 times 3 times x. And that I know how to do. 2 times 3 is 6 times x. 6x. Like that. So the associative properties can be used to simplify expressions where the operations that were originally there could not be done. But by rearranging, you get something that can be reduced down to a smaller, simpler expression. Now, the next property we look at is called the identity property of real numbers, or identity properties. There are 2 identities. They're not unusual numbers. They're numbers you're very familiar with. The number 1 is called the multiplicative identity. And 0 is called the additive identity. What the identity property says is the additive identity preserves the identity of an addend when added to this identity. Or more simply, if you add anything to 0, it doesn't change. So here, x plus 0 will just stay x. If you add 0 to anything, it preserves the identity of this object right here. So take an object, add the additive identity, it doesn't change it. The multiplicative identity does the same thing for multiplication. If you take something and multiply it times 1, it doesn't change. It stays the same x that you started with. When discussing the identity properties, you also can discuss the inverse properties. They are very closely related because they both involve the identities, the additive and the multiplicative identity. So here, the identity properties should also be joined by the inverse properties. I'm going to go ahead and put those separately. The inverse properties those tell you that if you have any 2 real numbers, let A and B be let A and B be real numbers where B is not equal to 0. Then, if you add A to its opposite, you're going to get the additive identity. So adding a number and its opposite give you the additive identity. Multiplying a number times its reciprocal gives you the multiplicative identity. Now here, that's the reason why we needed B not to be 0, because 1 over 0 would be undefined. Right? You can't multiply a number by something that's undefined. So the inverse properties simply state that if you add 2 things together and get 0, then those 2 things are opposites. Or if you want to think about it another way, if you add a number and its opposite, you're going to get the additive identity. For multiplication, it states if you multiply a number and its reciprocal, you're going to get the multiplicative identity. Or if you want to think of it another way, it says if you multiply 2 numbers and get the multiplicative identity, that means these 2 were reciprocals. Right? Here, this added to this gives you the additive identity. The way we say that is that this is the additive inverse. So here, a and negative a, so let's write it that way. Negative a is the additive inverse of a. Now, additive inverse is the formal name when it comes to using this property. However, a lot of times people use the word opposite. They have opposite signs. Same thing here. A lot of times people will say these are reciprocals, and that's a perfectly acceptable phrase to use. However, if we're being a little more formal about it, 1 over b is the multiplicative inverse of b. All right, now the next property we're going to look at seems a little bit more complicated at first until you realize that it's a property that you've seen over and over again since you first learned about multiplication. So in fact, let's start with just multiplication. Let's forget about identities for just a second. We'll get back to that in a moment. Let's say you're going to multiply two numbers. All right, let's say you're going to multiply 12 times, let's say 3. Keep it simple. 12 times 3. All right. Okay, so the way multiplication works, you're going to say 3 times 2. Okay, well, that's 6. Yeah? And then 3 times 1 is 3. Okay, so you get 36. All right, now, let's say I were to rewrite this. Let's say I was going to take 3 times 12. Well, it's the same thing. Right? 12 times 3, 3 times 12. We know that's going to give us the same answer. That's the commutative property. We can switch the order. Well, notice what this says. This is 3 times 12. Well, here, the 3 times the 1 gave us that 3. The 3 times the 2 gave us that 6. Just because these are left to right rather than up and down doesn't change how multiplication works. You can say that times that is going to give you 3, and that times that's going to give you 6. And of course, that still works. 3 times 1 is 3. 3 times 2 is 6, 36. Now, right here, I'm going to write this in a slightly unusual way. We don't generally separate numbers like the number 12 the way I'm about to, but there's nothing wrong with doing it. Let's say I wrote this instead of 3 times 12. Let's say I wrote this 3 times 10 plus 2. Okay, well, that still says the same thing. 10 plus 2 is 12, and then you're going to multiply by 3. Now, normally you would say, okay, well, why don't you just go ahead and add that and give you 12, right? After all, that's a single number inside of parentheses, make things simpler. But let's say I still followed this same pattern. After all, right here, 3 times that 1 gave us 3. Well, that number isn't really the number 1. Since it's in the tens place, it's really 3 times 10. Right? So, it's like saying we're going to split a check. You know, we went to a restaurant or something, and we're going to split up our bill, and we're each going to pay $12. Okay, well, there's 3 of us. Okay, so we're each going to put in a 10, and we're each going to put in 2 ones. Okay, well, then that's 3 $10 bills. It's going to be 30, and then 3 people are going to put in $2 each, so 3 times 2 would be 6. But all of that's going toward the same bill, so that's going to be 30 plus 6 is 36. And obviously it's still the same answer. I mean, we're still doing the same problem, 3 times 12. Here, this looks very strange. We would never really write multiplication this way, but it's not wrong. In fact, it's not any different from either of these. This is just vertical, horizontal. And here we did the strange thing of actually splitting it as 10 plus 2 rather than thinking of it as 12. But it's still correct, and it still gives us the correct answer. This right here, really all of these, but this is the one we want to focus on, this highlights what's called the distributive property of multiplication over addition. Because notice, if I changed this number to something else, or if I changed this number to something else, or even this number, the pattern would repeat. Let's say, for example, I had, let's go with 4 times 10 plus 1. Well, same thing. That's 10 plus 1 would be 11. 4 times 11 is 44. Okay, but let's say we thought about it this way. That's going to be 4 tens. That's going to be 40. And it's going to be 4 ones, which is just the number 4. And if you take 40 plus 4, that's the 44 that we had before. Notice that that works every time. If I replace any of these numbers with other numbers, it continues to work. So what happens if I replace one of these with a number that I don't know? Say, for example, I replace it with a variable. Well, as long as it's a number, I can continue to do this. Let's say I had something like 4 times, and instead of saying 10 plus 1, let's say I replace this 10 with an x. X plus 1. Okay, well then I still follow the same pattern. I have 4 times x, which incidentally I can't really simplify. I can't say, 4 times 10 is 40. 4 times x is just 4 times x. That's the best I can do. But over here, 4 times 1 is 4. And again, those are being added together. Now, unfortunately, I can't take it one step further and actually add those because I don't actually know what x is. But what I can do is I can multiply this out to simplify it down. Notice I have fewer terms to work with. I have fewer things. I don't have any more parentheses. And here, instead of having 2 multiplications, I only have 1. So I've simplified my expression down a bit. Let's say instead of just an x, let's say this was a 2x. So let's change things up a little bit. Let's say we have 5 times, let's say 3x plus 4. You can work really hard to come up with examples, 3, 4, 5. Well, again, it's the same thing. I'm going to multiply this, and I'm going to multiply this. Okay, so that's going to be 5 times 3x. Let me just write that as 5 times 3x. Plus, that's going to be 5 times 4. Okay. All right, now, we know 5 times 4, that's just 20. Here, 5 times 3x, remember, this is together. The 5 is separate, but because of the associative property that we saw just a few minutes ago, we can regroup these. We can say instead of 5 times 3x, we can say 5 times 3 goes first, and then we worry about putting in the x. And we know 5 times 3, that's 15. 15x plus 20. This is called the distributive property. Of addition, of multiplication over addition. I said that backwards. Of multiplication over addition. Basically, the multiplication comes over on top of the division, on top of the addition. Symbolically, the way that looks is if you have A times B plus C, this A multiplies the B, plus the A multiplies the C. All right, so here we can say, let A, B, C be real numbers. And notice we don't ever state what they are, nor does it actually matter. This will be true of any numbers. There is one more example that I want to show here about the distributive property. These are all examples of the distributive property. And that is, sometimes the number on the outside doesn't quite look like a number. For example, let's say I have negative 3x minus 5. Now here, this looks like you have, okay, well that's just a negative or a minus. How does that involve distribution? Well, think of the negative as being a negative 1. This is like saying negative 1 times 3x minus 5. And now it becomes apparent that, yeah, I can do the exact same thing. Negative 1 times 3x. Well, again, you can pull the numbers up together first. Negative 1 times 3 is negative 3x. And then negative 1 times negative 5, when you multiply two numbers that have the same sign, you end up with a positive. So 1 times 5 make 5. Just like that. So keep in mind that with the minus out here, you can think of it as being a minus 1, which gets distributed into your expression. One thing to note is usually whenever you apply the distributive property over addition, you don't need to write so much. Here, I'm the instructor, so that means I show all the details, every little bit. Usually, all this stuff is done mentally. you think, okay, 5 times 3 is 15, 5 times 4 is 20. So do keep in mind that you are free to write as much as you feel you need to, but the distributive property is often done mentally. As you're getting used to it, if this is the first time you've seen this, or if it's been a while since you've seen this, you might actually want to write out the first few steps. But as you get faster with it, keep in mind a lot of this will happen in your head. All right, so in fact, give this a try. Go ahead and multiply the following out. Go ahead and take negative 2 times 6x minus 4. Okay, go ahead and pause the video and unpause when you're done. All right, so we're going to distribute. Negative 2 times 6x. Well, negative 2 times 6 is negative 12 times your x. And negative 2 times negative 4 is positive 8. Just like that. And that's our result. Note that you're not limited to just 2 terms. You can actually do this with more terms. For example, you might have 3 times negative 6x plus 5y minus 4. Again, I work very hard to come up with examples. 6, 5, 4, 3. And again, the distributive property works the same way. 3 times negative 6x. Well, 3 times negative 6 is negative 18, so that's going to give us negative 18x. 3 times a positive 5, well, that's plus 15y. And then 3 times negative 4 is our negative 12. And there we go. If we had 4 terms, 5 terms, 6 terms, it wouldn't matter how many we have. Distribution works all the way down until the 3 multiplies each one of these. All right. Now, with these properties, we can start talking about and we can start simplifying algebraic expressions. Expressions are what are necessary to start talking about algebraic equations down the line. So what exactly is an algebraic expression? All right, so let's begin with some definitions. We begin with a term. Definition. So a term is the product or quotient. Now, it can be a quotient, but we won't see any of those now. For now, all of ours will be products. Product or quotient of one or more constant or variable. An algebraic expression is the sum of one or more terms. Okay. So here we're defining 2 things, terms and algebraic expressions. For example, something like number 5. That's a term because it's the product or quotient of one or more constants or variables. Notice it's one or more. So if you just have a single constant, that's a term. If you just have a single variable, that's a term. Or if you have a constant and a variable multiplied together, that's a term. If you have 2 variables multiplied together, for example, x times x, that would be a term. Generally, we don't write it as x times x. We write it as x squared. X times x times x, well, same thing. You would write as x to the 3rd. Generally, we don't write multiplication of variables as multiplication. We write it as a power. And if you were to take these 3 x's that were multiplied together and multiply them by, say, the number 2, well, that would also be a term. So here we have 1 term, 2 terms, 3 terms, 4 terms, and 5 terms. Now, there's nothing that says that these terms can't be negative. Here, I can say minus 5 times x. After all, that's a number times a variable. Right? So, we have 5 different terms here. You notice that some of them are just numbers. In fact, just this one right here. This is called a constant term. Whenever you have a term that is just a number, this is called a constant term. All the rest of these have at least one variable, and these are called variable terms. Okay, all of those together, each of those. Now, if you were to take these 5 terms and add them together, say 5 plus x plus negative 5x plus x squared plus 2x to the third, this would form an algebraic expression because you have the sum of one or more of these terms. Incidentally, since it's the sum of one or more, if I only took just that term, that on its own is also an algebraic expression. Any one of these terms on their own is an algebraic expression. But if you add several of them together, that also qualifies. This algebraic expression is made up of 5 terms. Note here you have plus and negative. Although that's not wrong, we generally just write that as minus. So here, we generally don't write plus a negative. We just say minus 5, like that. Neither of these are wrong. They both mean the same thing. Okay? Note that an algebraic expression is the sum of terms, not the difference. So here, if we're talking about this as an algebraic expression, it's understood that when we say minus, we mean plus a negative. But those are equivalent, so it doesn't really matter which way you want to think about it. Whenever you have a term that has a variable and a number in the front, say for example the minus 5, the minus 5x, this number in front has a name. It's called a coefficient. So here this term has a coefficient of negative 5. Now, if you have a variable by itself, say for example x, you say, okay, that doesn't have a coefficient? Yes, it does. It's the number 1. Because after all, x is the same as saying 1 times x. So if you have a variable by itself without any number, it's understood that there's a number 1 there. X is the same as saying 1x. So again, that's the coefficient. If you happen to have a number that's just by itself without any variables, well then the entire term is just the coefficient. So the number 5 is the coefficient. Now, whenever you have terms, you will sometimes have terms that differ only by the coefficient. The variable and any exponents are exactly the same. These are called like terms. Definition? If 2 terms have the same variable and exponent, and if they don't have an exponent, well, that's fine, but they should still be the same. They should still not have an exponent. If 2 terms have the same variable and exponent, or in the case of multiple variables, you might have an x and a y. Okay, variables and exponents. That's fine. You may have more than one later on down the line. If 2 terms have the same variables and exponents, the coefficients can be different. They can be the same. We don't say anything about those. Then those are what are called like terms. So for example, if I have an algebraic expression, 5x squared plus 3x squared plus 9x minus 5x, like this. This is an algebraic expression. Here, even though I have 4 terms, I have 2 of them that are like terms, and these other 2 are like terms as well. These are like because they both have the same x with the same power of 2. These are both like terms because they have the same variable of x without a power. Or if you like, you can say it's power 1. After all, anything to the first power is just itself. Whenever you have, so these are like terms to each other. And likewise, these are like terms. Like terms can be added together. You can kind of think of them like place values. When you have something like 12 plus 15, you don't just add all these numbers together. You don't say 1 plus 2 plus 1 plus 5. Right? You add together the ones that are in the same place value. The ones go with ones and the tens go with tens, right? 1 10 plus another 10, that's 2 tens. And 2 ones plus another 5 ones, well, that's 7 ones. Like that. You don't then add the 2 and the 7 together. Same thing over here. When you add terms, you only add the like ones. With regular numbers, that's like saying we're adding the ones with the ones and the tens with the tens and the hundreds with the hundreds. Over here, what we're doing is we're adding together the x squares to the x squares and the x's to the x's. So here, this can be simplified down. We don't need all 4 terms. We can combine them. The way we combine like terms is by combining their coefficients. Note, you can combine like terms by doing the arithmetic with their coefficients. Okay? This is the importance of vocabulary when you're studying math. Oftentimes you think computation, numbers are all that matter, but a lot of times vocabulary is important because here there's several vocabulary terms that unless you're familiar with them, it's hard to figure out what we mean. You combine like terms. Oh, what do you mean like terms? Oh, these are like terms and these are like terms. By doing arithmetic with their coefficients. What are coefficients? Those numbers right there. So, as our example, and here we're just going to use these terms. If we have 5x squared plus 3x squared plus 9x minus 5x, these like terms can be combined. You have 5 plus 3 will give us 8x squared. Here, that's a positive 9. That's a negative 5. Remember, think of that as plus a negative 5. So that would be 9 minus 5 would give us a positive 4. Keeping the sign of the number with a greater absolute value, the positive, like that. Notice that when you combine these, you combine the coefficients, the variable and the power remains the same. So 5x squared plus 3x squared becomes 8x squared, and 9x minus 5x is 4x. The variables nor the powers change, only the coefficient. Give that a try. Go ahead and combine like terms. 3x to the 4th power minus 5x to the 3rd power plus 8x to the 4th power plus 3x to the 3rd power minus 9x squared. Now, not everything's going to necessarily combine. Only the ones that are like terms. Don't force it. Only the ones that actually can go together. Go ahead and pause the video, give it a try, and once you have the result, come back and we'll confirm it together. All right, notice these are like terms, so 3 plus 8 make 11. The x to the 4th remains the same. We have minus 5x to the 3rd plus 3x to the 3rd, a negative plus a positive. We're going to subtract those numbers, keep the sign of the number with greatest absolute value. That's going to be a negative 2x to the 3rd. Notice this one is different from any of these. So this one doesn't combine with any of those terms. It simply remains minus 9x squared. And that's our result. We've combined our like terms. Like that. Should your numbers be decimals or fractions? None of that changes. And should your variables include multiple types of variables, not just x's, but maybe x's, y's, and z's, again, none of this really changes. So for example, let's say we had 3.4xy plus 2.5x squared plus 4.2xy minus 3.4x, like that. Note that in here, these are like terms because their variables are the same. Here, xy power 1. Here, xy also power 1. Those are like terms. Here, these are almost right, but their powers are different. That's a square, whereas this one's a first power. All right, whenever you don't have a power written there, that means power 1, because x is the same as x to the first power. So here, when we combine, we can only combine these two. Well, to combine, we're going to combine their coefficients. The fact that these are decimals rather than whole numbers or integers doesn't change that. Here, 4.2 plus 3.4 gives us 7.6 xy. This one and this one don't combine with anything, so you're going to leave them as they were. 2.5x squared minus 3.5x. And there we go. Finally, like so often is the case, what we can do is we can combine several properties that we've seen. We've seen how to distribute. Remember, distribution is basically like multiplication. And here we see how to combine like terms. Combining like terms is basically like addition. You're combining the ones that are like each other, just like you combine place values, ones with ones, tens with tens, hundreds with hundreds, and so forth. So what you can do is you can combine those to simplify. Simplify means use whatever properties are appropriate. Now, it's not a very specific set of instructions, but that's on purpose. It's so that you can use whatever properties are appropriate for that particular problem. Simplify means use whatever properties are available to you. Remember what we have. We have commutativity, associativity, we have distribution, we have combining like terms, and we're going to use those to reduce the number of terms to combine whatever can be combined and to make our expression as simple as we can make it. So consider the following example. We're going to simplify 2 times 3x plus 5 minus 4. Okay. Here, this 2 is going to be distributed. It's being multiplied. Here, this minus 4 is going to be subtracted. Okay. How do I know what order to do it in? It's the same order we always do things. The order of operations. Parentheses, exponents, multiplication, division, addition, subtraction. Now, here, parentheses normally goes first. But, you notice there's nothing you can really do in here. You can't add 3x plus 5 because they're not like terms. One has an x and one does not. So parentheses would normally go first, but since there's nothing you can do with those, well, then you move on to the next thing. Next would be exponents, but, well, we don't have any. So really, the first action that we can take is multiplication. So here, we're going to take this 2 and we're going to multiply it there and there. By distributing, we're going to take 2 times 3x, that'll give us 6x. And then 2 times 5 will give us 10. And now we can do addition and subtraction. Here we can combine like terms. Notice that these are like terms. They're both constants without any variables. This is different from either of these because this one has a variable x. So when we combine like terms, only these can be combined, and we end up with 6x staying as it is, plus 6 when you combine. So that expression has been simplified down. Notice we have fewer operations. There's no more distribution to do. There's no more parentheses. And here, everything's been condensed down to a single plus. You know you're done simplifying when none of the properties apply anymore. Here, we can't. There's nothing to distribute. There are no more like terms to combine. Changing the order of things using commutativity, that wouldn't help. That wouldn't do anything. So that is as simplified as our expression will get. These expressions can be simple with only one or two actions to perform, or they can be made more complicated, but it doesn't change how this works. Consider 3x. Oh, here we're doing the same thing. We're going to simplify. So let's write that out, simplify. You're going to simplify, or we're going to simplify 3x minus 5 times, we're going to open our brackets, we're going to have 3x minus 2, we're going to open parentheses, x plus 8. We're going to close our parenthesis, we're going to close our bracket, and then we're going to say minus 9. Okay. Now this looks very, very complicated, but handling it one step at a time using the order of operations, we can simplify this down to something much cleaner and much more condensed and much easier to understand than this. All right, so following the order of operations, note that parentheses go first. Okay, so all the stuff in there. And notice that within those parentheses, there are more parentheses. So we will start focusing there. Okay, but there's nothing to do there. X plus 8, those can't really be added because they're not like terms. Okay, so let's zoom back out. Here we normally would think to do parentheses first, right there, but parentheses can't really be done because they're not like terms. So what else can I do next? Well, here I have multiplication, because this is 2 being multiplied times that, and I have subtraction, because I have 3x minus that stuff. Okay, well, the order of operations tells me multiplication should always go before subtraction. Multiplication, division before addition, subtraction. So let's go ahead and handle that. Let's take this 2 and multiply it times the x plus 8, which we'll do by distributing. Okay. Now, that negative is part of the coefficient. So here you can think of this as plus a negative 2. So when you distribute, that negative will come along with the 2. So here this will be 3x minus 5 times, open bracket, 3x. The negative 2 times the x is negative 2x. And the negative 2 times the 8 is negative 16. Okay. All right, well, we're still in the brackets. We've done our multiplication. We did that by distributing. But now we can do our addition and subtraction, because here we have some like terms. Now remember, don't force it. Only combine what can be combined. Here, these are like terms, but this is not. So only combine what is eligible to be combined. Here, these two go together. So that'll give us 3x minus 5 times. 3x minus 2x is just 1x, which you can write 1x. However, whenever we have 1x, generally we just write x. You can write 1x, and that means the same thing. This minus 16 is not a like term, is not like to these terms. So that's just going to stay as minus 16. Okay. All right, now, we wish we could do that subtraction, but we can't because they're not like terms. So that means we're done with these parentheses. Okay, so now what? Well, after parentheses, we look outside of the parentheses. We don't see any exponents, so we can skip that. What's next is I see some multiplication right here, and I see subtraction and more subtraction. Okay, well, multiplication or division would always come before any addition or subtraction. So the next thing we're going to do is we're going to handle this 5. So let's distribute 5 times x and 5 times 16. Oh, I guess I should say negative 5, because that negative is part of the number, is part of the 5. So when we distribute, it's going to carry that negative with it. So the 3x, we're going to leave it alone for now. But minus 5 times x is minus 5x. Now, careful here. A negative times a negative, that is now a plus. 5 times 16 is 80. Again, negative times a negative made that a positive. When you multiply two numbers that have the same sign, you end up with a positive answer. And then that minus 9 comes on down. Finally, I notice addition, subtraction here. Notice that not all of this addition or subtraction needs to be done, or even can be done. Here, these are the only like terms to each other, and these are the only terms that are like each other. So here, we wouldn't be able to do this final addition. So going from left to right, we do the operations that we can. Here, 3x minus 5x, that's going to be negative 2x. Remember, if they have opposite signs, you're going to subtract them. 5 minus 3 is 2. And then keep the sign of the number with the greatest absolute value. Here, I have 80 minus 9, 71. keep the sign of the number with the greatest absolute value, so it'll stay positive, 71. And I wish I could simplify that further, but since I don't know what x is, these are not like terms, I can't combine them. So that is as far as I can go. So this expression condenses down to minus 2x plus 71. When you start solving equations, you'll have equations that involve lots and lots of terms. Those terms make solving equations complicated. So before we ever solve equations, what we do is we simplify the expressions in the equation. Because if you're going to solve an equation, what would you rather solve? Something that looks like this equals to a number, or something like this equals to a number? That will be much more complicated. So simplifying is used to make your problem smaller and easier to handle before you start solving. So go ahead and give this a try. Go ahead and simplify. Let's see, minus 2x plus 3, like that, plus 4 times 6x minus 1. Like that. Okay. Go ahead and pause the video, simplify, and then once you are done, go ahead and unpause and we'll go through it together. Alright, so parentheses would normally go first, but notice inside these parentheses there's nothing you can do. These are not like terms. You can't add them. Same thing with these parentheses. There's no like terms. Okay, so there's nothing you can do about that. There are no exponents. So really, the first operation we're going to handle is multiplication. Here, there are two instances of multiplication. You'll notice that this 4 can distribute out through here. Here, this minus is like saying minus 1. And that minus 1 should distribute through here. So let's go ahead and do both of those. If I take minus 1 times 2x and minus 1 times 3, well, that'll be minus 2x, and that'll be minus 3. Now, if I distribute the 4, that's going to be 4 times 6x, that'll be 24x, and then 4 times negative 1, that'll give us negative 4. Okay, so we've done all of our multiplication. So now we can handle our addition and subtraction. Notice not every addition and subtraction can be done. Only the like terms can be combined. So notice here, these two are like each other. I have minus 2x and 24x. They're the only ones that have an x. Here, these are different from those. These are just constant terms. So this one would combine with this one. So in the end, minus 2x and 24x, well, that's 24 minus 2 is going to give us 22x. Notice the variable doesn't change, only the coefficients. And here, combining these numbers, we're going to have minus 3 minus 4. Okay, that's the same as saying negative 3 plus a negative 4. So you're going to add the two numbers, 3 and 4 make 7, and then keep the negative from those two numbers as our result. So in the end, this simplifies down to 22x minus 7, just like that. And that is the end of this topic here. If anybody has any questions, comments, or problems, please make a note of those, reach out, and I hope everyone has a nice day.